Welcome all of you. Now let us start the last unit, that is fifth unit, time varying fields. Time varying fields. So our fifth unit is time varying fields. Until now, whatever we have dealt in our starting units, that is electrostatics or magnetostatics, they are all time invariant fields. Suppose our first unit is electrostatics and our second unit is magnetostatics. Magnetostatics, they are all, we have dealt with the time invariant fields. Time invariant fields. We are dealing with the time invariant fields. Okay, that means they are not varying with respect to time, they are all constant. But when we are coming to this last unit, we are dealing with the time varying fields. Okay, time varying field means that field is produced with the current that is varying with respect to time. That field is produced with the current that is varying with respect to time. Suppose if you are taking static electric field, that is produced by electric charges, which are at rest. Your static electric field is produced by electric charges which are at rest. Okay. Now, if you consider the static magnetic field, then they are produced by the electric charges. They are produced by the electric charges that are in motion, and which are moving with constant velocity. Okay. So if you deal with your first unit and second unit, the electrostatics and magnetostatics, they are time invariant fields. Time invariant means they are not varying with respect to time, and also electric field and magnetic field. Electric field and magnetic field are independent. Electric field and magnetic field are independent of each other in this first unit and second unit. Time invariant fields means the electric field and magnetic fields are independent of each other. Okay. And also static electric field is produced whenever the electric charges are at rest, and static magnetic field is produced whenever the electric charges are in motion, but if they are moving with a constant velocity. Okay, so this is the information about the time invariant fields in our first unit and second unit. But here last unit deals with time varying fields. So time varying field is produced by the currents which are varying. Time varying field is produced by the currents which are varying with respect to time. Okay, time varying field is produced by the currents which are varying with respect to time. Now in this last unit we are going to study about the time varying fields. So how we have defined the time varying fields? Time varying field is produced by the currents which are varying with respect to time. So with this information, let us proceed to the equations derivations in your fifth unit, that is time varying fields. Here first we are going to deal with Faraday's laws of electromagnetic inductions. Faraday's laws of electromagnetic induction. So what does this Faraday's law states? So if we see the definition, whenever the flux linked with a circuit, whenever the flux linked with a circuit is varied, whenever the flux linked with a circuit is varied, an EMF is induced. So how we can define the Faraday's laws of electromagnetic induction? Whenever the flux linked with a circuit is varied, whenever the flux linked with a circuit is varied, that means how we can represent the variation of flux mathematically means just we can differentiate it. Whenever the flux linked with a circuit is varied, an EMF is induced. That means if you vary this flux d phi by dt will produce some EMF E. Okay, E proportional to d phi by dt, and the induced EMF is directly proportional to the rate of change of flux. And what does our Lenz's law state? Lenz's law states that every result opposes the cause that produced it. That means what is the result here? The induced EMF is the result. What is the cause that produced it? Variation of flux. Now this result will oppose the cause that produced it. That means E equal to minus d phi by dt. So E proportional to minus d phi by dt is the final expression for Faraday's laws of electromagnetic induction. Suppose if there are n number of turns in that circuit, then we can take E equal to minus n d phi by dt. E equal to minus n d phi by dt. So what does our Faraday's law states? Faraday's law states that whenever the flux linked with a circuit is varied, an EMF is induced. Okay, whenever the flux linked with a circuit is varied, an EMF is induced, and the induced EMF is directly proportional to the rate of change of flux, that means d phi by dt. And Lenz's law states that every result opposes the cause that produced it. That means you should keep minus. So if you remove that proportionality, we can say that E equal to minus n d phi by dt. Minus n d phi by dt. Okay. So this is the expression for Faraday's law of electromagnetic induction. So we got that Faraday's law of electromagnetic induction is represented mathematically as E equal to minus n d phi by dt. And in statement we can define this as whenever the flux linked with a circuit is varied, an EMF is induced. Okay, and the induced EMF is proportional to the rate of change of flux, and the induced EMF also opposes the cause that produced it, so we are keeping minus sign. Suppose if you are considering a single turn alternator, that is take n equal to 1, then E equal to minus d phi by dt. Suppose in our first unit from work and potential, we already defined the in work and potential difference V equal to minus integral E bar dot dl bar. For this induced EMF, we already kept minus sign, so this minus of minus will give you E equal to integral E bar dot dl bar. And what is phi from our magnetostatics? What is phi means? Flux phi is equal to surface integral of b bar dot ds bar. Surface integral of b bar dot ds bar. So that is the expression for flux phi. Now if you substitute that here, if the expression for induced EMF is integral E bar dot dl bar, and flux phi is surface integral of b bar dot ds bar, and if you substitute that in this equation Faraday's law, what is E value? Integral E bar dot dl bar, integral E bar dot dl bar is equal to minus d by minus d by dt of derivative of what is the phi value? Phi value is integral b bar dot ds bar. Integral b bar dot ds bar. Okay. Now we can clearly observe from our first unit, we know that induced EMF can be defined as integral E bar dot dl bar, and from our second unit we have defined the flux phi as integral surface integral of B bar dot ds bar. Now if you substitute that in this Faraday's law expression, that is, take this equation 1, take this as equation number 1. Suppose if I am keeping this E and phi values in this first equation, what is E value? Integral E bar dot dl bar. What is phi value? Surface integral of B bar dot ds bar. So E value I am substituting integral E bar dot dl bar, and minus d by dt of what is phi value? Phi is integral B bar dot ds bar. Okay, phi is integral B bar dot ds bar. So this is the integral form of Faraday's law. This is the integral form of Faraday's law, which is very important. I am writing it as equation number 2. So what is the integral form of Faraday's law? Integral E bar dot dl bar is equal to minus d by dt of integral B bar dot ds bar. Now anyway, if Faraday's law is to be satisfied, and if you want some EMF to be induced in a circuit, then first what is to be done? This flux should be varied, magnetic field should be varied, then only the EMF will be induced. So what are the conditions in a circuit or in an alternator for the flux or magnetic field to vary and for the EMF to be induced? For the EMF to be induced, then what are the conditions means? The first condition is stationary closed loop. Stationary closed loop, that means stationary conductor. Stationary closed loop and time varying magnetic field. So general form of Faraday's law is E equal to minus n d phi by dt. Suppose if I take single turn alternator, n is equal to 1, then E equal to minus d phi by dt. We already know that E equal to integral E bar dot dl bar and phi equal to integral B bar dot ds bar. If I substitute this E and phi values in this first equation, then E value is integral E bar dot dl bar and minus d by dt of phi is B bar dot ds bar. So integral B bar dot ds bar I am substituting. This is the integral form of Faraday's law of electromagnetic induction, which is very important. Next, for the EMF to be induced in a circuit, then flux or magnetic field should be varied. If at all the magnetic field is varied, then only some EMF will be induced. So for the EMF to be induced in a circuit, so what are the conditions that are possible are stationary closed loop and time varying magnetic field. Stationary closed loop and time varying magnetic field means it will come under the category of statically induced EMF. Statically induced EMF. Okay, so we have already defined in our previous subjects that statically induced EMF means whenever the conductor is stationary and the flux is varying. Whenever the conductor is stationary and the flux is varying, then the induced EMF is called as statically induced EMF. So your first case is for the EMF to be induced, stationary closed loop, that means stationary conductor and the time varying magnetic flux density or time varying magnetic field. That means here magnetic field is varying and conductor is stationary. That is statically induced EMF case. So here, how you can represent this mathematically in equation form, we should see. When the conductor is stationary, that means stationary closed loop, and the magnetic field B is varying, that will come under the category of statically induced EMF. So here, what is the integral form of Faraday's law of electromagnetic induction? Integral E bar dot dl bar is equal to If I send this derivative inside, then if I send that inside, surface integral of dou b bar by dou t. I am giving only partial derivative, dou b bar by dou t dot ds bar dot ds bar. So just I am improving this equation. Integral e bar dot dl bar is equal to minus, this is the surface integral of dou b bar by dou t dot ds bar. Okay. Now what is Stokes theorem? By applying Stokes theorem in our second unit, by Stokes theorem, line integral can be converted to surface integral. So by applying Stokes theorem for our second unit, we can convert the line integral here to the surface integral. So for converting that line integral to surface integral, so if I convert this, then you will get del cross E bar dot ds bar, because by using Stokes theorem I am converting this line integral to surface integral. Okay, E bar dot dl bar can be converted to del cross E bar dot ds bar, that is equal to minus surface integral of dou b bar by dou t dot ds bar. Suppose if ds bar and ds bar are equal, then what is del cross E bar? So integral are equal, because this is also a surface integral, this is also a surface integral. I am converting that line integral to surface integral by Stokes theorem. So del cross E bar is equal to minus dou b bar by dou t. So this is the mathematical representation of Faraday's law of electromagnetic induction when your conductor is stationary and magnetic field is varying. When your conductor is stationary and magnetic field is varying, then what is the Faraday's law representation? Del cross E bar equal to minus dou b bar by dou t. Del cross E bar equal to minus dou b bar by dou t. So this is the mathematical form of Faraday's law during statically induced EMF case. That means stationary closed loop and time varying magnetic field. Del cross E bar equal to minus dou b by dou t. Suppose if you consider static magnetic field. Static magnetic field means your magnetic field is stationary, constant. Then what is the derivative of a constant? Then it will become 0. Del cross E bar will become 0. For a static magnetic field, del cross E bar will become 0. Okay. So what is the Faraday's law first case for the EMF to be induced? We are considering the closed loop or conductor is stationary and the magnetic field is varying. Then by using this mathematical form of Faraday's law, just I am converting the line integral to surface integral by using Stokes theorem. So E bar dot dl bar can be written as del cross E bar dot ds bar, and right hand side you will have minus surface integral of dou b bar by dou t dot ds bar. So if I equate all this on comparison, what is del cross E bar? Del cross E bar is minus dou b bar by dou t. This is the Faraday's law mathematical representation. Del cross E bar equal to minus dou b by dou t. Suppose if you take static magnetic field. Static magnetic field means your magnetic field is constant or stationary. So on what is the derivative of a constant? That will become 0. Del cross E bar is equal to 0. Okay. So this is the first case. If I go to the second case, that is dynamically induced EMF. Dynamically induced EMF, that is the second case of Faraday's law. Dynamically induced EMF means the closed path or conductor is moving closed path closed path or conductor is moving closed path, and stationary magnetic field. Stationary magnetic field, that means B bar. Stationary magnetic field. So what is the first case? That is statically induced EMF, where your closed path or conductor is stationary and your magnetic field B bar is varying. That is statically induced EMF. The example for that is transformer in the case of statically induced EMF. Now for dynamically induced EMF, what is the condition? The conductor or closed path should be moving. That means your conductor is varying and your magnetic field is stationary. Stationary magnetic field B bar. So in this case, how we are going to represent the Faraday's law of electromagnetic induction? So here consider a charge Q. Consider a charge Q which is moving. Consider a charge Q which is moving in a magnetic field. Which is moving in a magnetic field B bar. Consider a charge Q which is moving in a magnetic field B bar with velocity V. With velocity V. Then what is the force that is experienced by the your charge Q is given by force that is experienced is given by Q V bar cross B bar. This is the force that we have already seen in your third unit. The force experienced by a charge Q which is moving in a magnetic field B bar with a velocity V. With a velocity V is given by force is equal to F bar equal to Q V bar cross B bar. Okay. Now what is the electric field intensity E? The electric field intensity E is given by F by Q. Already we know this in first unit. What is electric field intensity E? E is given by F by Q. That means Q V bar cross B bar by Q, that is equal to V bar cross B bar. Now what is your equation? The induced EMF is equal to integral E bar dot dl bar. Integral E bar dot dl bar. So here I am taking the electric field intensity as EM. So what is EM? EM is V bar cross B bar cross B bar dot dl bar. Okay. So this is the dynamically induced EMF condition for Faraday's law of electromagnetic induction. What is the statically induced EMF condition? First condition, that is del cross E bar is equal to minus dou B by dou T. For the first condition, del cross E bar is equal to minus dou B by dou T. This is the statically induced EMF, first condition. That means your closed path is stationary and the magnetic field, and the magnetic field is varying. For that first condition, that is statically induced EMF condition, del cross E bar should be equal to minus dou B bar by dou T. For static magnetic fields, we are taking this as 0. What is the second condition? Your conductor or closed path is moving and your magnetic field is stationary. So for that, what we got? E equal to V bar cross B bar dot dl bar. Integral V bar cross B bar dot dl bar. Okay. So this is the first case and this is the second case. And what is the third case for your Faraday's law? Both the closed path as well as the magnetic field B bar are varying. Moving closed path and varying magnetic field. So in this condition, that means both your conductor is also moving and your magnetic field B bar is also varying. Both your conductor is moving and your magnetic field B bar is also varying. So here the induced EMF In this condition, the induced EMF is equal to the first case EMF plus the second case EMF. First case EMF is transformer action, statically induced EMF, transformer EMF plus motional EMF. Second case is dynamically induced EMF. So in the third case, both moving closed path as well as varying B bar, the induced EMF is equal to transformer EMF plus motional EMF. That means statically induced EMF plus dynamically induced EMF. So your total induced EMF will be equal to integral E bar dot dl bar, integral E bar dot dl bar, that is nothing but the induced EMF. Induced EMF E equal to integral E bar dot dl bar equal to what is the magnitude of the transformer EMF? If you consider only magnitude, leave this sign, this just indicates the Lenz's law. If you consider only magnitude, that is dou B bar by dou T. Our first equation, first transformer equation is, first statically induced EMF case is integral dou B bar by dou T dot ds bar. That is the first case EMF that we got on comparison. That means this first case, before comparison, what we got? Integral del cross E bar dot ds bar is equal to minus integral dou B bar by dou T. So integral del cross E bar dot ds bar is equal to minus integral dou B bar by dou T dot ds bar. So just I am writing this magnitude, okay, here dou B bar by dou T dot ds bar plus what is the motional EMF? Integral V bar cross B bar dot dl bar, integral V bar cross B bar dot dl bar. So what is the induced EMF in the third case? That means both the closed path is moving as well as your magnetic flux density is also varying. Magnetic field is varying, conductor is also varying. Here the total induced EMF is the sum of the first case statically induced EMF case transformer EMF plus second case dynamically induced EMF motional EMF case. So total induced EMF is equal to the sum of the statically induced EMF or transformer EMF and motional EMF integral V bar cross B bar dot dl bar. So these are the three cases: statically induced EMF, dynamically induced EMF, and third one is both, combination of both representations of Faraday's law of electromagnetic inductions. And these equations are very, very important. So on comparison, in this first case, when the conductor is stationary and magnetic field is varying, what is the expression? Del cross E bar is equal to minus dou B bar by dou T. This comparison, on comparison, del cross E bar is equal to minus dou B by dou T. This equation is very important. And what is the complete transformer EMF? That means induced means dou B bar by dou T dot ds bar. And in the second case, dynamically induced EMF, what is the induced EMF formula? Integral V bar cross B bar dot dl bar. So I am writing that here. In third case, we are adding both first case EMF and second case EMF. That means when both conductor is moving as well as your magnetic field is varying. So these are the three cases for Faraday's law of electromagnetic inductions. These formulas are very important. Mainly this del cross E bar is equal to minus dou B bar by dou T. Del cross E bar equal to minus dou B bar by dou T. This equation is very important.